Right, so good afternoon, everybody, and welcome. Thanks very much for joining us this afternoon to hear Dr. Ruchi Gupta from the University of Birmingham, who is going to be speaking to us about her research into label-free optical biosensors. And as you may know, each year we invite distinguished speakers from around the world who are shaping the future of chemical engineering, the profession, and its research agenda. And this year, we're very pleased to invite speakers from our own department to open the session, following which we will hear from Dr. Gupta. And after the lecture, we'd like to invite you to drinks, a reception in the CPSC common room. And for those of you who don't know where that is, you have to exit here, go to the end of the corridor, make your way up to the 6th floor. And I think without further ado, I'd like to introduce our first two speakers. They will each speak for 15 minutes. Right, 15 minutes, followed by questions, and you're going to be looking after that, right? So the first speaker will be Sam Davies, and he's a PhD student from the SIA-NOL group, and he's going to be talking about optical sensors for biomarker monitoring. Over to you.
Yeah, cool. Do you want to start passing that round? Right, hello. So my name's Sam Davis. I'm a PhD student for SIA-NOL. I'm a first year PhD student. I've just started at Imperial, and I work on developing optical devices for the continuous monitoring of metabolites within the bloodstream, or the body as a whole. So our group, basically the main goal of our thing is develop optical sensors for applications in medical settings, but this can also branch over into industry, but our main drive is towards medical settings. So a question for all of you, and I will pick on one of you if you don't give me an answer, is what is an optical sensor? You've got 30 seconds for someone to put their hand up. Go on.
Sensors based on optical light?
Yes, thank you. So optical sensors are basically just any device that uses light as a medium to measure through. So we basically work on holographic sensors, fiber optic sensors, and wearable sensors. And I'll take you through some of the different things that we work on at the moment. So I basically predominantly am working on holographic sensors, and these sensors are basically polymers that are nanostructured to be sensitive to different analytes in the bloodstream. We've got a temperature-sensitive contact lens which uses cholesteric liquid crystals to sense temperature in the eyes. Then we've got a pH-sensitive contact lens and subdermal tattoo biosensors, which is where inks are impregnated under the skin and they change color depending on changes in your extracellular fluid in the dermis of your skin. And then alongside this, we also work with we basically develop apps which are able to read these changes quantitatively depending on the color that's observed in the change in structures. So my work is predominantly based on traumatic brain injuries. So there's traumatic brain injuries come in two stages. So there's the primary injury, which is where you walk into a lamppost, you fall off your bike, or you're in a car crash and your brain bounces off the inside of your skull. That's the primary injury. There's nothing much really when you go to a doctor's that can really happen to change that. And a doctor is predominantly working to stop you getting these secondary injuries, which is where you get blood in your brain, you get pressure increases which cause the brain to swell up against the side, and this can lead to all of these different problems such as cell death and inflammation, etc. And these kind of injuries are obviously they can happen to anyone with a brain. It's just a thing of life. But then as well as that, they're more common in countries with really relaxed safety laws where, for example, you've got people on motorbikes without helmets as a regulatory law. People come off their bike at 20 miles an hour and they get one of these injuries. So this is the current technology that's currently used to monitor these kind of injuries when you get them. So we've got invasive intracranial pressure monitoring. So this device is really good. It can measure pressure, but what you have to do is you have to trepanate someone's head and then measure the pressure within the brain. They can measure pressure really well, but they can't really give you information about the biomarkers that are going on inside your brain, which can kind of give you indication about why the brain is swelling. So this device is useful, but not ideal. And then after this, we've got extraventricular drains. So these devices basically go into the lateral ventricle of your brain and work as a siphon. So what they do is the brain fluid's pumped out and they have to keep your ears level with this zero pressure, which is not as easy as you'd think. It requires constant attention from doctors and nurses, but also if you sit up, you can siphon all of the CSF out of your brain, or it can flood your brain back with CSF, so they're not exactly the best thing that you can use, but they always are used really. And again, it gives you no data about the biomarkers, and the pressure measurements can be unreliable due to that change in height issue. Finally, we have microdialysis of CSF. So this is where a synthetic CSF fluid is flooded into a semi-permeable membrane that's inserted inside the brain. You get diffusion of biomarkers across this membrane, and then the analyte that comes out with the dialysate can then be run through a clinical chemistry analyzer to observe the changes that have occurred in that solution. They do give you information about the biomarkers, but there's a really low sampling frequency because you can't keep on taking samples from the brain. And then also, the clinical chemistry analyzer can be the other side of a hospital, which means that the data that you get can be out of date by the time you get back to be able to change something in the patient. So it causes a delay in patient treatment. And also the clinical chemistry analyzer is extremely expensive, so they cost a lot of money. And also, so all the devices I've just shown you are reliant on some form of metallic part, which basically means that an MRI machine works as a massive magnet. And if you put a magnet inside of a magnetic field, a piece of metal inside of a magnetic field, you get two effects. One, it interacts with the magnetic field, which then causes the image that you get from MRI to become distorted, which can lead to misdiagnosis of things. And then also, it starts to heat up, which if you've got metal inside someone's brain and it starts to heat up, you can basically start to cook their brain from the inside out, which obviously we want to try and avoid. Next one. So this comes into where our research works. So we work on holograms. So these are nanostructured double polymers holograms, which basically have no metal involved, and it's a change in refractive index on the same order of a wavelength of light. So this refractive index means that you can reflect certain wavelengths, which is, works via Bragg reflection. So the way that we use these devices to make sensors is we incorporate groups that are capable of binding different biomarkers, such as this one, which is used for acids, ions, and then for glucose. And upon binding of these ions or metabolites, you end up with either an increase or a decrease in the spacing between these two, this refractive index, which changes this delta value, and then changes the peak that you see through the Bragg, through the reflection. And from this information, we can quantitatively tell the different concentrations of ions and sugars and different things within the brain. So the reason these devices are better than the current technology is that they're entirely polymer, so they can go into MRI machines. They're real-time measurements because the sensing is inherently built into the polymer. It means that you get real-time measurements, so you don't have to worry about taking a sample, taking it to a lab, and then bringing it back to be able to get measurements of the patient's brain chemistry. Light is the only stimulant requirement, so that means that it doesn't require metal wires, which means that it doesn't interact with the MRI. The fiber is flexible and biocompatible, which means that you have less risk of inflammation and you have less risk of hemorrhaging from inserting the actual cable into the person's brain. There's no recalibration, as I'm sure a lot of you are aware. If you have electrochemical cells, you need to recalibrate by putting it back into a standard solution. These devices don't require that. And then also, the quantitative results can be measured using a photometric device, which is something as simple as the camera on your mobile phone, from the color of the wavelength that you get out. And then to show you how these devices could be applied, we have so something similar to if you had a cerebral microdialysis machine, you could shine light with the fiber optic submerged in the dialysate, and then you'd be able to read the measurements that you get. And then as well, you could put this device on the end of a 2x1 coupler and then observe the reflected light through this output terminal, and that would be similar to inserting an ICP probe. And just to let you know, the thing that you're passing around, that's a hologram, which is similar to the ones that we make, but it's not sensitive to different metabolites. So then I'm going to take you on to the contact lenses that we work on. So this is the current gold standard that's used in measuring ocular fluids. So it's called the Screamer's test, and it basically involves putting blotting paper under the patient's eyelid and then timing the response to fill that with tear fluid. There are a number of issues with this. Basically, if you stimulate tear fluid in your eye, what happens is that the tear fluid becomes a different composition to the tear fluid that's normally on your eye. So it's not representative of the actual eye, of the tear concentration. And then also trying to extract this fluid from this piece of paper can lead to issues because you can end up with different complex processes to remove this solution. So it's not really that reliable. Another one is basically that they use tubes, and this tube is basically put on the side of the eye. The irritation is significantly less, so the tear fluid's a little bit more representative of the actual tear fluid, but it's also from the edge of the eye rather than over the cornea. And when you measure ocular concentrations, you really want it to be from the cornea. So some of the biosensors that we've worked on are basically eye temperature, glucose concentration, and pH, and I'll take you through some of these now. So this is a method that we have for measuring eye temperature, where basically we use a laser to ablate a small hole, pour in a cholesteric liquid crystal, cure it with UV light, and then we end up with this small sensing area, which you can see here. So these cholesterol molecules were basically, we change the ratio of these three R groups within the composition, and that changes the temperature at which they melt. So when these form crystals, they form in these helix structures, which you can see here, and have a different pitch where there's a repeating unit. And by changing the temperature, you basically increase or decrease the disorder, which then leads to a change in this repeating unit and changes the reflected light that you observe, which is seen from this. So then, we also have these 4 points that go over the cornea, and by measuring all over the cornea, you can get an average of the temperature within the cornea, which gives you a much more representative information about the eye temperature. We also have glucose measurements. So these basically work on a very similar prospect to the holograms that you saw before, but they work on a diffraction grating, which is basically that this D-spacing here is imprinted in the synthesis of these hydrogels. And then what we do is we incorporate boronic acids. Upon introduction of glucose, these boronic acids bind the molecule and then begin to expand. This then changes the D-spacing and changes the first order and zero order diffraction level. And by measuring the difference between these two diffractions, you can actually quantitatively measure the glucose concentration in the ocular fluid. And this could be useful in different things such as diabetes, glaucoma, and a number of other illnesses. So it's really helpful to understand. Then after this, we also have anthocyanins. So these are basically so this molecule is present in red cabbage, in loads of different vegetables, and it's a very common antioxidant. But we coat this onto a contact lens, and dependent on the pKa of these two protons, we end up with deprotonation at different pHs. So we end up changing the electronic structure around this anthocyanin group, and then the change in electronic structure changes the color that you observe when this molecule is exposed to light, which you can see here. So it can move all the way from pink all the way down into the blue. And then that means that you can measure the temperature, the pH within the patient's eye. And this is ideal for things such as like ocular ASIA and for dry eye. And then finally, I'm going to take you on to the dermal biosensors that we use. So this is a modern application of the 4,000-year-old tradition. We basically impregnate colorimetric or color-sensitive molecules underneath the skin in the dermis rather than in the epidermis or the hypodermis, because this area is closely related to the arteriole, the venules, and the lymph nodes. So that means you get cross-diffusion around this area, and it's quite representative of the whole body as a cross-section. It's better than putting a dermal patch because obviously you've got to get all the metabolites through the skin and then onto the skin surface. So it's a much better method of measuring devices. So have I missed anything? Yeah, so then finally, we also use, so we've done this with a number of different molecules. So we have pH sensors, glucose sensors, and albumin sensors, all of which can be sensed with a mobile phone device. So this is with an app that we've developed. And upon putting this molecule, which is the pH sensor, which is bromophile blue, under the skin, the deprotonation of this sulfonic group changes the color of this molecule under the skin, which means that you can get a colorimetric response to be able to understand the different chemistry that's going on under the skin. Yeah, so these devices are basically beneficial because you end up with a relatively non-invasive treatment for different conditions. So you could measure without having to take a blood sample and other different methods that are quite invasive of the patient. You can end up measuring the glucose concentration, and the patient will be able to see quantitatively by taking a photo with their phone, but also qualitatively by actually looking at the tattoo and being able to see a change in color, which could give them a pre-warning that they're about to go hypo or hyperglycemic. I think I've actually run a little bit early, but that's the end. Sorry about that. So thank you very much.
Our next speaker is Dr. Ignacio Moya. He's a postdoc from the Polizzi group, and he's going to be talking to us about biosensors to detect RNA integrity biomarker monitoring.
Okay, well, thank you very much for giving me the opportunity of briefly talking about our project that I started first in Clio's Contour-AFD group and then with Karen Polizzi, both of them here in the Department of Chemical Engineering. So, well, we are developing a sensor to detect the degradation on RNA molecules. Okay, and this project is motivated by the recent growing the interest about RNAs as active molecules, especially in pharma industry. So here I'm showing you two examples of two different companies, Moderna and CureVac, that are developing a wide variety of different drugs that have as an active molecule RNAs. Okay, so all of them, as I'm saying, are RNAs, and well, they target a very different kind of diseases. So, for example, cancer, immune diseases, or maybe also vaccination. And well, you can see that they are at different development stages, but already in 2018, two of them, patisiran and inotersen, were approved by the FDA, and this third one that I'm not going to read was approved last year. So there are already some products that seems quite promising. And also I wanted to mention this company, Greenlight, which is offering a product to control the population of some insects in crops. So they just do it with using RNA. So this is quite advantageous because you don't have the side effect of contamination, pollution by some chemicals, just omitting the idea that you are exterminating a whole population of insects, but just one, okay? So it's not that bad. But okay, so the thing is that they might find a lot of application, these RNA molecules. And if this is true, if this turns up as a good opportunity, this will imply that the production scale of RNA will grow in the coming years. And this will need some quality control assays accompanying to this to be conducted in parallel to this bigger scale production. Okay, and this is particularly important in RNAs because these molecules are quite sensitive to the degradation, specifically by the action of some enzymes called RNases that are in most of biological samples, and they act so fast. So even with the contact with the skin, we can ruin a whole batch of RNA. So you have to be extra careful when you are synthesizing RNAs. So a proper way of assaying whether our RNA has been degraded or not, this might be needed in the future. So at the moment, this is a problem that has been solved for a few years in a lab scale. So we can use spectrometry combined with gel electrophoresis to assay or to test how our RNA is. But these technologies are not very sensitive. I mean. So imagine that you have a chain of 1,000 nucleotides and you lose the first 10 of them. So you won't see that on a gel, on standard gel electrophoresis. It is not sensitive enough. And maybe this nucleotide missing will suppose a big change on the activity of these molecules. There are some other alternatives, more sensitive, like microfluidic electrophoresis. So it's basically the same principle, but they offer better sensitivities. However, when we go to bigger size of RNAs, we again lose sensitivity. And we need like expensive equipment for doing this. Also, we can use quantitative PCRs, but these techniques also require a lot of steps. They are very specific for a single molecule, needs a lot of optimization, so they might not be the best option if we want to quickly and accurately test the integrity of our RNA molecules. So, considering all of this, what we are trying to do is develop this biosensor to detect whether an RNA molecule has been degraded. We are focusing on messenger RNA, mRNAs. And we want this biosensor to be suitable for on-field application by people who has not been specifically trained. It will be basically something like this common use glucose test, or also like a pregnancy test, something that everyone can use with any specific training. And this, of course, will involve that we need to get rid of most of the equipment needed, or maybe minimize it maximum possible. Okay, so we came up with this design of the biosensor, which have three main parts. The first one is a solid support. The second element of the sensor is the RNA that we are testing, and the third one is this protein. This is a chimeric protein which combines two functions. The RNA recognition and binding function and a reporter function. So we have fused two different proteins, so in one single molecule we have two roles. And this is the key of the biosensor. So how it works? Initially, we have this solid support that is functionalized with an oligo. This is a short DNA molecule that is complementary to the end of the RNA chain. This is a poly-A tail, which is present in all mRNAs. So we will bind our RNA to the solid support. And later, the protein, the chimeric protein, will recognize a specific sequence or nucleotide on the other part, on the other end of the chain, on the 5' end. Okay? So at the end of the assay, we will have attached these three elements, one to another, and just with a magnet we can remove them from the liquid, from the sample. Okay? And then is when the reporter protein starts to do its job, which is degrading a chemical called nitrosamine. Okay? So initially it is yellow, and if we have this beta-lactamase on the media, it will turn red. Okay? So if we have our full-length RNA, everything will be attached, and at the end we will have this thing, this enzyme, degrading our chemical. In the case of any degradation, what will happen? We will lose either one end, the 5' end of the RNA molecule, or the other end, this one here, or both of them. In any case, either the RNA will not bind to the solid support, or the protein will not bind to the RNA. That will mean that later when we do the colorimetric test, the reporter enzyme will not be present, so we will not see any shift on the color. So this is basically how we have designed our sensor. Looking at it in a little bit more of detail, we came up with two different designs. The first one, and they differentiate in the RNA recognition element. So in the first element of the part of the chimeric protein. So in the first design, we have been using a peptide that recognizes an RNA hairpin. So this is a specific RNA folding that is produced when we have a specific sequence of nucleotides. So this lambda N peptide recognizes this hairpin. In this case, it is called Boxby hairpin, and binds to it. So we fuse this hairpin to the 5' end of the RNA molecule. And for the second design, we are using a cap binding protein. This cap is a structure found in some mRNAs, and I will come back to this later. First, I want to show you some results. And this is the response of the first design of the sensor. Okay? So what I'm showing here is the absorbance, meaning the change in the color from the yellow to the red, at different percentages of full-length RNA. So imagine that you have a sample of X moles of RNA having different proportion of full length on it. And this is how the sensor responds. So you can see that we have sensitivity to differentiate between different percentages of integrity on the RNA samples. Also quite important, we almost don't have any background level, which is something also desired when you are designing a biosensor. You want having like a flat signal when you are supposed to not detect anything, like in this case. And if you see also, it shows also an important property, which is like linearity. So for a specific time, the response of the sensor is linear, has a linear response, versus the percentage of complete or not degraded RNA. So that was nice. But, so this result I'm showing here, the first is the same one that the initial before, is for a short RNA chain of 250 nucleotides. If we use bigger RNAs, you can see how the sensitivity of the assay decreases. Okay, so this is not good, although we can still use it to detect whether we have degradation in longer RNA chains. Okay, and now, as I said at the beginning, we are trying to make our system compatible with on-field application. So this is how it will look like just using a visual inspection. So this is a fast-forward video, and you can see how the higher the full-length RNA we have, the faster the nitrosamine is degraded. So you can just assay this with your eyes. So with a proper calibrated background, you could even estimate the percentage of degradation on your sample. Okay, and now I'm explaining a little bit about the second design. As I said, we are using this cap on the RNA as a target. This cap structure is quite important. It's very relevant for the RNA activity, and it's a challenge analytically and also when we are synthesizing RNA. So imagine that we have a chain again of 1,000 nucleotides. How will you know that you have added this specific nucleotide, which is, I forgot to mention that you first synthesize the whole chain of RNA and then you add this on top. So it can be difficult analytically to know whether you have added this. So you can, there are some mass spec methods. Also you can do RNA-seq, but it's not simple, it's quite work demanding. So we wanted to test our system with this issue as well. And we just modified the sensing protein by this cap binding protein. And well, after a long time, I was close to drop this project, but at the end, luckily, it started to work. And funny, it works better than the other one. So you can see here that from RNAs ranging from 250 nucleotides to more than 10 times bigger, we still keep the same sensitivity on the system. And here, this is something equivalent to the previous result. So here we have 0% of cap RNA, 100% of cap RNA. Okay, so quite nice. And yeah, the response for these three sizes is linear. It's kind of almost the same. And just to show you this, finishing with this, well, this system, since we are using the same reporter enzyme, is equally suitable for doing a visual inspection. And also we have been testing or assaying how to improve the dynamic range of the sensor, meaning with dynamic range the difference between the background level and the signal. And this is of special relevance when doing visual inspection, as I was saying. Basically, just simply increasing the nitrosamine concentration, we can do that, which is what I'm showing in this graph. So this orange line is the concentration that I have shown for all the previous results, but if we double or quadruple it, we could increase the dynamic range on the response of the sensor. And that's it. Just conclude acknowledging Cleo Kontoravdi and Karen Polici's group, our collaborators in St. Mary's Hospital, and all of you. Thank you.
Right, so now it's my pleasure to introduce our distinguished seminar speaker, Dr. Ruchi Gupta, who is a senior lecturer and Birmingham Fellow in the School of Chemistry at the University of Birmingham. And previously, she was a lecturer in Analytical Science at the University of Hull. Dr. Gupta attended the Nanyang Technological University in Singapore for her undergraduate studies in electronics and electrical engineering on a prestigious SIA-NOL scholarship. She then completed her MSc in engineering physics at McMaster University in Canada, where she developed the basic components of generic and programmable microfluidics. This was then followed by a PhD and a Royal Academy of Engineering Enterprise Fellowship at the University of Manchester. So the research theme, as you'll discover from today's seminar in Ruchi's group, is polymeric optical sensors. They design internally referenced transducers and associated instrumentation to analyze species of interest in real samples and real environmental conditions. And the applications are sensors in point of care and point of use analysis. So I think without further ado, Ruchi, over to you.
Thank you. Okay, so yeah, I will skip the introduction. Thanks for the introduction. The research in my group, the overarching theme is optical biosensors, and I would like to start by saying what's a sensor. So a sensor is defined as recognition elements that are in physical contact with the transducer. And when I say recognition elements, they could be phages, antibodies, aptamers, enzyme substrates, so basically any analyte responsive probes. And the transducer converts this analyte recognition element binding into an easily measurable signal. And if we have an analyte or recognition elements that are of biological origin, that's when we have a biosensor. Okay, so transducer, in my group, we make transducer out of mesoporous hydrogels. So the hydrogels have pores in the range of tens of nanometer. And this allows us to attach recognition elements in the volume of the hydrogel rather than just on their surface. Hydrogels also offer additional benefits, and some of these benefits are, firstly, we can tune their chemical diversity to immobilize recognition elements. We use solution processed fabrication, which results in more affordable devices. And finally, many of these materials are biocompatible. So these are particularly useful for wearable biosensors. And in my group, we in particular work on label-free optical biosensors, so which means that we rely on a universal property of analytes called refractive index to do the measurements. So if we look at a transducer schematic, we have recognition elements in it, and this would have a refractive index given by n, which is the real refractive index, and is related to the ratio of speed of light in a medium to that in a vacuum, and k, which is the imaginary component of refractive index, and is related to losses in a medium. So it could be because of absorption, for example. And if an analyte binds to these recognition elements, there is a change in either a real or imaginary or both refractive index. So this change is directly proportional to the concentration of the analyte, allowing us to do quantitative measurements, and the binding between the recognition element and the analyte is in dynamic equilibrium. So if you imagine that your sample is around the transducer, if the concentration in the sample changes, then the transducer signal would update itself. So we can do continuous monitoring. So yeah, quantitative and real-time monitoring. But we cannot measure refractive index changes directly. So this is where transducers come into scene. And in my group, we have been working on 3 different types of transducers, and hopefully I will be able to cover all 3 of them, at least to some extent. So the first one is gratings, the second one is interferometers, and the final one is waveguides. So I will start with gratings. You may already know this, but I will go through it briefly. So gratings are alternating strips of materials with alternating refractive index. And when light falls on this structure, it diffracts. So we can define something called diffraction efficiency, which is, for example, the first order. It's the ratio of intensity in the first order divided by the intensity in the 0 order. And this diffraction efficiency, it depends on the refractive index contrast between the alternating strips. So we can attach recognition elements selectively in the alternating strips, and as the analyte binds, it changes the refractive index contrast between the strips, and this in turn changes the diffraction efficiency. So by measuring the change in the diffraction efficiency, we can know the concentration of the analyte. So we did not invent this. The diffraction sensors have been known for ages. But currently, the hydrogel gratings, they are made either using soft lithography or photolithography. And this is a 2-step process, where in the first step, first strip of materials are deposited, and then the gap between the strips are filled in the second step. Also, because hydrogels are quite soft materials, you cannot make high aspect ratio structures very easily using this process. So the aspect ratio is limited to less than or equal to half. We want to have high aspect ratio structures because we want to have thicker structures so that we can attach lots of recognition elements in this structure, and we would like to have fine pitch gratings because that defines how well the diffraction orders are separated. So in my group, we were keen to develop a fabrication approach where grating sensors can be made in a continuous layer of hydrogel to open up the possibility of making high aspect ratio structures. And our solution is a photofunctionalizable hydrogel where the functional groups are initially blocked by a chemical molecule, which is shown by these pink circles. So when light falls on this hydrogel, the regions where the light falls, the pink circles are selectively removed, leaving behind the free functional groups such as amines in this case. We can then react these free functional groups with recognition elements to create a pattern of recognition elements. So when I came up with this idea, my hypothesis that we will be able to create sufficient contrast, refractive index contrast between the alternating strips by using this approach. And this in turn required us to incorporate high density of photoremovable protecting groups, so lots of pink circles in the gel. We needed an aqueous chemistry to preserve the optical properties of the hydrogel. And finally, it would be nice to be able to pattern using 4 or 5 nanometer light because lots of light sources are available at this wavelength. So we looked in literature and we found that one of the most commonly used functional group to protect amines is this NVOC, where this chloroformate groups reacts with primary amines to protect them. But NVOC is water insoluble, and this chloroformate group hydrolyzes in water. NVOC also absorbs in 365 nanometer, so it's commonly used with a sensitizer called thioxanthone to increase its absorption wavelength to 4 or 5 nanometer. But again, this molecule is water insoluble. There is a byproduct scavenger which is used with this chemistry, and this is the only compound that was available commercially and is water soluble. In terms of the hydrogel, for this work we decided to work with polyacrylamide. So we have a monomer called acrylamide and a crosslinker based acrylamide, and you can polymerize them by using free radical polymerization. So polyacrylamide is quite nice in some respect because we can polymerize it with other comonomers to form copolymers. Okay, so this is the water-soluble monomer that we synthesized to make the photofunctionalizable hydrogel. So if we look at this bit, this is NVOC, which is protecting the primary amines. And then we incorporated quaternary ammonia to increase the water solubility of the monomer. And then we have this methacrylate group so that we can copolymerize it with acrylamide. To increase the water solubility of thioxanthone, we added this PEG. And if we look at the absorption spectra of these two compounds, so NVOC is this black trace, and as expected, it absorbs at 365 nanometer, and the red trace is for thioxanthone PEG, which absorbs at about 4 or 5 nanometer. So they work similar to the water insoluble counterparts. And this dotted trace is the fluorescence emission of thioxanthone PEG, and this is to make sure that the absorption and emission do not overlap a lot, because if we want to have high spatial resolution for patterning, the two spectra should not overlap. Okay, so then we mix acrylamide and this water-soluble photofunctionalizable monomer and put the cross-linker to make our photofunctionalizable hydrogel. We then looked at the photolysis kinetics. So we acquired the absorption spectra of the hydrogel, and this black trace, it's coming because of the presence of NVOC in the gel. And that's why it has a peak absorbance at 365 nanometer. Then we expose it to 405 nanometer light in the presence of thioxanthone, and we can see that the peak is decreasing. So we can then plot the peak absorbance as a function of time to get the time constant, which is about 90 seconds. In terms of the spatial resolution, we created the free amines and then reacted them with fluorescein isothiocyanate so that we can do confocal microscopy. So this particular image is using 35 micron thick hydrogel, and I think it's not so visible, but the pitch of the grating is about 10 micron. So this means that we were able to create structures with an aspect ratio of 3, which is about 6 times more than what's currently reported. Okay. So once we have attached fluorescein to the gel in a pattern, we have an amplitude grating. So we can look at the diffraction efficiency. So if we shine a laser light 532 nanometer and look at the diffraction pattern on a camera, this is what we get. So the diffraction efficiency is about 5%, which can be related to the difference in the transmission of the alternating strips, or the difference in the absorbance of the alternating strips. So 5% corresponds to a difference in absorbance of 0.5. And then we can also plot rate of change of diffraction efficiency, which is the sensitivity versus the difference in absorbance between the strips, and we get a curve like this. So it has an optimum about 0.3, and for our device, we are somewhere here. So not fully optimized, but close. Okay, so just as a proof of principle for sensing, because fluorescein is pH sensitive, its absorbance is pH sensitive, we put in solutions of different pH and look at how the diffraction efficiency changes. So this is a plot of change in diffraction efficiency as we put in solutions of different pH. So this is to show that we are able to monitor pH changes in real time using this approach. Okay, but the long-term aim of the project is really to attach recognition elements such as antibodies rather than maybe using dye-based molecules. So that's what we are working on at the moment. Also, this project is in particular to make the sensors for wound monitoring. So these sensors are to be placed in a dressing, and all the results that I have shown you so far interrogates the grating in the transmission mode. But if we want to be able to use them for studying wounds, we want to be able to interrogate these sensors in the reflection mode, so that the skin is on this side and we can do all the measurements from the other side. So this in turn requires us to design porous reflecting layers underneath the sensor so that the wound fluid can reach the sensor. So that's another aspect that we are working on. The reason I have put this slide is because if there is any interest in this work and there is any expertise, then I would be very happy to talk about this. Okay, so the next one is interferometry, where the basic principle is if we have two point sources of light, then they interact to produce peaks and troughs in intensity. So we can think of these point sources as hydrogel pillars as well. And we can attach recognition elements in one of these hydrogel pillars so that when the analyte binds to these recognition elements, they introduce additional phase shifts. And these phase shifts are translated into change in peak or trough pattern in this. So I will do a quick movie just now, but if you see that the two yellow lines initially they are in phase, and as the analyte binds, which is reflected in the movie as the translation of this yellow line, there would be a change in the pattern. So we can see how the pattern changes when the analyte binds, and similarly when the analyte is desorbed, the pattern would go back to its original Okay, so now we can imagine instead of hydrogel pillars, we have hydrogel filled channels, and in this case, we will get a stack of fringes in the third dimension. So this dimension of the fringes give us information on what's happening along the length of the channels. So we can get some special information. But if we fill the channels with hydrogel, diffusion is not a very good way to drive molecules because it can take days or at least hours. So we use electric field to drive samples in the hydrogel filled channel, and this speeds up the process to few minutes. And I will show you that as the analyte such as protein moves in the channel, we can monitor in real time how the protein moves in the channel. So this is where the protein comes in, and okay. So how do these interferometers compare against existing interferometers? So there are such as McMaster waveguide interferometer. So in this case, the McMaster interferometer, the light travels along the arm of the waveguide, whereas in our case, the path length is determined by the thickness of the channel. Okay, so the path lengths here are much shorter. So they are about at least 36 times shorter. So why have we made the path length shorter? Well, one of the reasons is our sensor allows us to do imaging, whereas McMaster interferometers are point-based sensors. So if we look at the limit of detection, so we put in solutions of different BSA concentration. So this one I have to say that this is without attaching any recognition elements in the channel. So the limit of detection is without any amplification because of the recognition elements. And this is 7.6 micromolar. So if we attach the antibodies, usually it's amplified by 10 to 4 to 10 to 6, depending on how many antibodies you can attach in the channel. Okay, so since our path length is much shorter, another way to improve the limit of detection is to combine electric field driven pH steps with these techniques. So what do I mean by that? All proteins, they are amphoteric. So they have an isoelectric point at which they are neutral, and because they have no charge, they can't move in the electric field. So if we imagine a channel where one of the reservoir is filled with base and the other with acid, we can have a protein plug, and as we apply the electric field, a pH junction would be formed because of the movement of acid and base. And if our acid and base pH are chosen correctly, at this step it would match the isoelectric point of the protein. So the proteins can concentrate at the junction. I will show you this in the interferometric setup because I think it's easier to see. So this is in the presence of discontinuous buffer electrolytes, and we can see that as the protein moves in the channel, it begins to focus, and that's where the intensity of the fringes increases. And we think that this happens because the proteins are so concentrated that it creates some sort of a lens effect. So this is, I think, somewhere here. Yeah, it will stop, it will get focused. Okay, so using this approach, we are able to, this is another way of looking at the same thing. So I'm plotting the change in that intensity with distance over time. So here where the protein band is formed. In this case, we used 20 volts to drive the protein along a centimeter length of the channel. So it took about 13 minutes. But usually people apply about 100 volts. Okay, so using this approach, we can concentrate the protein by a factor of 1,000 to further improve the limit of detection. Okay, so just to wrap up this work, in terms of the current ongoing work, the idea is to form this protein plug using this continuous buffer electrolyte, and then we have these recognition elements immobilized in the channel. So then the plug would be moved towards the recognition element to do the final detection. But the formation of these discontinuous electrolyte system is not as trivial as I described. It's quite hard actually. So in the long term, what we are working on is to have a channel filled with a continuous layer of hydrogel and then use patterns of light to create the pH patterns. So they are immobilized pH patterns. And then we can also shine light to selectively attach recognition elements at the places where we would like. Okay, so this brings me to the final topic, which is waveguides. So the waveguides we have been working on for a long time now, and these waveguides, they comprise of few micron thick hydrogel film on a glass substrate, and the work that I will present today is with immobilizing a dye in the waveguide. These waveguides are different from conventional waveguides in the sense that the refractive index of this hydrogel layer is intermediate to the substrate and the cover. So light is partially confined in these waveguides, and at resonance angle, if we look at the reflectivity curve of this structure as a function of angle, at resonance angle we see a dip in the reflectivity curve. And this is because of the presence of dye in the waveguide. The position of this resonance angle is a function of the refractive index of the cover layer and of the waveguide at a fixed thickness of the waveguide and at each wavelength. So the idea is we can attach recognition elements in the waveguide. Then when we put the sample, certain analytes would bind to these recognition elements, and then there are these interfering species, unwanted species. Hopefully they are unbound. And then when we do a wash, the unbound species are removed, leaving behind the bound species. So at each step, we can monitor the resonance angle with time, and after washing, the shift in resonance angle is proportional to analyte concentration. The work that I will present today has been done using chitosan. The waveguides were made of chitosan, which is a polysaccharide with primary amines, and these are useful for attaching dimolecules, for attaching the recognition elements, and also for cross-linking. So these waveguides we created just by spin coating. So we dissolve chitosan in acetic acid and spin coat at 900 RPM. And this is how a typical device looks like with 25 by 25 millimeter glass square, and the thickness of the waveguide is about 1.5 micron with a refractive index of about 1.344. So I will show you one potential application of this waveguide. We are interested in measuring serum ferritin and its average ion content. So ferritin is an intracellular protein, and its presence in serum at high levels indicates problem. At the same time, it's thought that ferritin in serum contains less iron than what it should when it's present in the cells. But currently there are no techniques which can do the concentration measurement and its ion level in a single step. So you need two different techniques to do the measurement. So we were keen to determine protein concentration and its ion content in a single step. And our hypothesis is the protein concentration is determined by the refractive index at a selected wavelength. And if we look at refractive index versus wavelength, so this means the optical dispersion of the protein, then it's a function of its average ion content. Another way to look at it is, so apoferritin is ferritin with no ion. Apoferritin would have certain refractive index, and the refractive index of ferritin is because of the protein plus the refractive index of the ion atoms present in it. And because ion absorbs strongly in the visible light, as shown here, so this means that its imaginary refractive index is strongly wavelength dependent. And based on Kramer-Kronig relation, the real and imaginary refractive index are connected. So this means that the real refractive index of ion and hence that of ferritin would also be strongly wavelength dependent. Okay, so the idea is, this is a schematic of our instrumentation. This is our waveguide that we mount on a prism, and then we have a white light which is like a wedge, which means that we are illuminating the waveguide with a range of angles of incidence simultaneously. We look at the output by passing it through a grating and capturing it on a camera. And this is how the output looks like, where the x-axis is wavelength and the y-axis is the range of angles of incidence. So we can see that we are able to get the output between 416 and 678 at the same time, which is not the case for all sensors. So for example, SPR works above 650 nanometer. And this range is limited by the area of the sensor of the camera chip, not by the operation of the waveguide. The waveguides can operate between 320 nanometer and 950 nanometer. So this black line is the resonance angle as a function of wavelength. And we can measure the change in resonance angle at each wavelength to determine the protein concentration. And we can measure the slope of this black line with wavelength to know the optical dispersion of the protein. So the first bit has been done by lots of label-free biosensors. So I will only focus on the latter part. Okay, so we attached anti-ferritin in the waveguide, and then we put in 110 nanomolar of either apoferritin or ferritin. We let them bind, and we can see that the shift in the resonance angle for apoferritin is much lower than for ferritin. The other observation is the shift because of apoferritin is largely wavelength dependent, whereas with ferritin it's wavelength dependent. So both of these observations are attributed to the presence of iron in the protein core. And we can support this by looking at information from literature. So if we look at the refractive index value of ferritin and apoferritin at single wavelength, 587 nanometer, then for apoferritin, it's about 1.6 times 10 to minus 4, and a ferritin with maximum number of iron atoms is 4.36 times 10 to minus 4. So we can do a calibration curve where we plot the ratio of refractive index versus the number of iron atoms, and it follows a straight line. So I wanted to see how many iron atoms are present in the ferritin that I used in this work. So I read this calibration curve. So if I take the shift in resonance angle for ferritin at 587 nanometer and divide by apoferritin, I get 2.29, and by reading this calibration curve gives me 3,375 iron atoms in the ferritin that I used. I also did the same measurement using UV-Vis, and that resulted in about 3,560 iron atoms. So there is about 5.5% difference, but at least it gives me some confidence that I can use my waveguide biosensor for this purpose. Okay. Then there was another calibration curve where I'm plotting the change in resonance angle at each wavelength divided by the change in resonance angle at 586 nanometer. So the open circles are for apoferritin and the closed circles are for ferritin. And the slope for apoferritin is about 10 times lower than that of ferritin with 3,375 iron atoms. And if we have a protein where the iron atoms is in between 0 and this, the slope would be intermediate. So we can write the relationship between the slope of this curve and the number of iron atoms, and it's given by this expression. So for any unknown protein, if we can do the same curve, we can use this relationship to then determine the number of iron atoms. Okay, this is just to say that the sensor is specific, because when we put BSA, the signal, although BSA concentration was 100 times higher, the signal was 5 to 10 times lower. Okay, and the limit of detection, it's about 700 picomolar. And we let the protein to bind for an hour. So how can we work at lower limits of detection? Well, one way is to again combine the electric field driven pH junction. And we have shown this in another work where we showed that the protein concentration is increased by a factor of 600 to 930 in less than a minute. Okay, so the results that I showed you are with this lab-based instrument, but we have now also developed this 3D printed instrument, which is about 16 by 13 by 11 centimeter, and it weighs about 800 grams. So now we are testing our sensor chips using this 3D printed instrument. Do I have time or?
Yes.
Yes, okay. Okay, so far I showed you all the measurements after doing the washing, but it's also useful to do real-time measurements. In this case, the primary challenge is the resonance angle would change because of temperature and the sample composition along with the analyte binding. So how can we deconvolute these two? And to show that how big the problem is, if we look at the change in refractive index of water with temperature, the thermal refractive index coefficient is about 10 to minus 4 refractive index unit per Kelvin. This is not a small number because with analyte binding, the change is in the order of 10 to minus 8 to 10 to minus 5. And similarly, interference, the change in refractive index is usually much, much higher than because of analyte binding. Okay, so current sensors such as SPR usually account for this challenge by having a reference channel in proximity to a sensor channel. So they are about a millimeter or more apart. But if we look at the response of the sensor channel against the response of the reference channel, the slope of this curve is not quite 1. So this means that the two channels are not quite the same. And because the solution has to flow from the sensor channel to the reference channel, there is a time delay in the solution to travel, and this causes these kind of artifacts, which makes it difficult to extract the kinetic information. And finally, because the sensor and reference channel are separated in the order of millimeters, it takes about several seconds for temperature differentials to equilibrate. Whereas at the micron scales, it takes tens of microseconds for temperature differentials to equilibrate. So considering these, we have designed a waveguide sensor where the reference waveguide is placed underneath the sensor waveguide. So in this case, the two are separated only by a couple of microns. And we designed the thickness and the refractive index of the waveguides in such that one of the mode is largely confined in the top waveguide, and the other is largely in the reference waveguide. In this case, we are using monochromatic light instead of white light. So the output, the y-axis is angle, but the x-axis is distance. So this gives us information along the width of the channel. So one of these black lines corresponds to the resonance angle of the sensor, and the other one corresponds to the reference. If a particle falls during the fabrication process, then it creates these kind of defects in the output. Okay, so the idea is we can do the differential measurement between the reference and the sensor to eliminate the effect of temperature and sample composition, but still measure the analyte binding. So to show that, we attached IgG in the sensor waveguide, and this bit is from the sensor and this is the reference. And here we just recirculated streptavidin. So these are absolute signals, and we can see that the absolute signals are just horrible because of the recirculation. But if we look at the differential signal, they are so much cleaner. Okay. So in the differential signal, the signal is reduced by half, but at the same time, the signal to noise ratio is improved. So to mimic the effect of interference, we put in different concentrations of glycerol, and again we can see that the differential signal is about 50 times smaller than the absolute. And the temperature, we varied by 10 degrees, and the differential is about 10 to 20 times smaller based on how much the temperature is varied than the absolute. So in my opinion, 10 degrees Celsius is a huge temperature change, because in the commercial sensors, they maintain the temperature difference to about 1 millikelvin. Okay, so the final remarks. I showed you a grating-based sensor where we have developed a photofunctionalizable hydrogel for making those sensors. I talked about interferometric biosensor integrated with electrokinetic sample pre-concentration. And finally, the waveguide-based biosensor, where I talked about their application for measuring ferritin and its iron content, and an internally referenced biosensor. So thank you. Oh yeah, this slide should have been before, but okay. I would like to acknowledge my group and also the various funding bodies and our collaborators. And yeah, thank you very much for listening.
So I guess we were talking earlier today when I met you about the structure of the hydrogel.
Mm-hmm.
So maybe tell us a little bit about how the structure and how engineering the structure can provide a big impact on what
yes, I did not present that part. Yes. So the chitosan work that I present, we control the drying time between spin coating and rehydration. So once the solution is spin coated, the films are wet, and if you let them dry out, they would not swell back to their original structure. So we control how long we dry them before we rehydrate, and that helps us to control the porosity of the gels. So a lot of my research is also on designing porous hydrogels, which is not a trivial task actually. And we are also moving towards synthetic hydrogels because they can be dehydrated and then reswelled, which is much easier in terms of storage.
Great, thanks for that. Okay, if there are no more questions, I think we should thank our speaker one more time. Thanks very much.
Thank you.
It was a great presentation. Thank you.